intraoral scanning and 3D printing, what it has done to dentistry and orthodontics. A bit of history. The dental casts we use in orthodontics and even dentistry were invented in the 1700s by a German dentist. It's been a very long time, and they're still very accurate, and there's nothing wrong with them, except for the fact they're a solid piece of plaster and they're not easily manipulated. Then 200 years later, Dr. Broadbent introduced the cephalogram, and from then Dr. Steiner in 1952 introduced one of the first cephalometric analysis. Then in 1972, Dr. Andrews, Larry Andrews, introduced the straight wire system. In 2010, the aligner finally took over. Invisalign had introduced the concept in 1998 or 1997. And now in the 2020s, Orthodontics 4.0, which is based on artificial intelligence, is now making inroads into the profession. You can see that there is some significant changes, but it took a long time. In 1993, I was able to use a commercial laser system to get my first 3D model of a dental cast. It had 70,000 points and took 24 hours to complete because every layer had to be manually manipulated and placed one on top of each other. And in 1998, 99, I think, the tabletop scanners came into the market, and in 2011 the iTero machine was introduced, which was the first intraoral scanner. The lab bench scan models that you see on the right hand side were just produced from an original impression, poured in plaster, and then scanned. At the time we just thought that they would be replacing our solid models and save us some storage space. We didn't think that it would make such a massive impact on the profession, and it actually became a revolution. Then in 2011, the intraoral scanner was introduced with the iTero 1, and nowadays I would argue that the majority of orthodontic offices in North America are using intraoral scanners. They don't even have one, they have multiple scanners, because this technology is very efficient, but it has also some drawbacks. Said in 2011, I bought my first iTero machine. This is the one, and you had these two pedals where the green was to move forward, the red was to move back. So what you had to do, you had to scan one scan at a time, and at the end the iTero machine will recompute all the little pieces of scan in the mouth and reformat the whole arch. Scanners for models, which are interesting, but again, due to the fact that we nowadays scan the majority of our patients, we don't have a lot of use for that except for scanning older models or doing some prosthodontic work on plaster models. That is still relevant today. The problem that we also have is price versus quality. It looks like the price has been going down dramatically of these scanners. This has happened to be a 3 shape, which was a very, and still is a very good brand of scanners, fairly expensive, and the quality has come up. And the software has changed dramatically to help us do better, faster. So nowadays there are a lot of Chinese or Asian scanners, or even American ones, that are much cheaper than the, I would call them, the most known brands. They seem to be doing acceptable work, but you got to be careful because what you see on the screen may not be the accurate representation of the dentition. This is a scan. So the big difference between the human brain and the computers is every single point here has an XYZ coordinate, and all these XYZ coordinates are in a 3D axis. So that's a lot of coordinates, and the computer will calculate and join these points, and that will create a tooth. Unlike a dentist that looks at a model or a patient, sees a molar, a premolar, or an incisor immediately, the computer has to be taught that this cloud of points represents a molar, a premolar, or an incisor. The computer also has to learn to differentiate between different shapes of molars and different shapes of premolars, because they are slightly different, and not better understand what is the exact geometric representation. But the big advantage of XYZ coordinates, it allows us to write programs to move these coordinates in space, and this is when Invisalign was born. What do we create with an intraoral scanner? You can read this text by stopping the video, but an STL file on OBJ, but usually STL is what you will be getting when you are scanning a patient. Is really important is it's only the surface. If you have an STL file and you cut it in the middle, there is nothing inside. So it's only a surface. The big advantage of that is it does not occupy a lot of space. It's not a big file, it's only a surface file. So you have a cloud of points, and then they are joined together by triangles, and it has the XYZ coordinates. So in space, you know exactly where each end of the triangle is. An STL file is going to be corrupt if it cannot be completely sealed off. You cannot have open triangles in an STL file. The STL file is not a printed file. It's just a file that can be manipulated in all sorts of different ways. So when you buy a 3D printer, every single 3D printer will take an STL file and reformat it into its own proprietary software. What an STL file is, it's a cloud of points that cannot be printed. A printer will print layers like pancakes. The printer will take the STL file, which is a cloud of points, like so, and it will make little pancakes of different thicknesses between 50 and 100 micron, or even 170, depends on the printer. Usually in orthodontics we use the 100. Little layers of information that the printer now is able to decipher and print. The big misconception of STLs, and by the way you can see all the triangles, and a very interesting one because all the triangles are almost the same size, which is not always true depending on the morphology, but the big misconception of STLs, and especially for us in orthodontics that we're used to move teeth and even in dentistry, is that the computer sees teeth, and you can see that's not the case. We have a bunch of triangles. Every single one of them, as I told you, has to be joined. So there is no interproximal space, the same as you would kind of see in a dentition. So this is not really the reality. The computer has to join these points to get to the complete STL file. So the first misconception, this is one unit, it's one STL file. The teeth cannot be manipulated. Some other things of importance is, if you look again, the interproximal space is not defined. So the computer will have to learn to define where is the interproximal surface of the second molar and the first molar. That works really nicely when the teeth is straight like this, but when the teeth are crowded, overlapping, it's a much more complicated process. Something else too, in this case, you can notice that these triangles are different from the other ones. That tells me this is not real. The scanner was not able to get into this pit, and what the computer has done, it's called reformatting. So it just basically filled the hole using a program in the model of jean-marc. That's a problem, because you will see that if you put the mask, meaning you remove the triangles, you will think that this is the shape of the tooth, and it's not. Something else, when you get a very quick STL like this one, and the patient hasn't been told to brush their teeth, hasn't been very diligent, you get this type of an image. The computer may be able to clean that. So this is the tooth, absolutely. This is tooth structure. This is plaque. And you can also notice that the triangulation here is different, because the computer is trying to close down the STL to make sure that there is no void into the file, can be manipulated correctly. So all these happen from the back end. My advice to you are twofold. The first one is make sure the teeth are really clean in order for you to avoid having this kind of strange triangulation that should not be there. And the second thing is I usually blow some air to try to clean as much as possible the interproximal space in order to have the scanner penetrate as far as possible in between the teeth to get a better interproximal triangulation, to get the most efficient segmentation that we can get. If you look on the left hand side, this happens to be an STL. We took the real STL and see there is a diastema right here. The computer has to fill it. If the diastema is large enough, it will just fill this space here and it will fill this space here. But in this case, maybe there was a little bit of saliva or some form of reflection for the scanner, because remember the scan uses light or laser beams, but mainly light to go towards the surface, and it rebounds, and the rebound is actually what is captured. So probably some form of saliva or something. So the computer decided there was structure there, and it made a complete file with these triangles. But then you go to the other side and you say, well, this happens to be arch form and this happens to be Invisalign. Software for arch form decided this was tooth, so there is no more diastema, which will be very careful to check your representation or your computer images of the patient's dentition, because sometimes there'll be some discrepancies. This is one. Invisalign picked up the diastema correctly. But then you have the second problem. But there was this very significant hyperplastic gingiva here. Arch form picked it up pretty well, but look at Invisalign, didn't pick it up at all. It reformatted. So that's what I'm trying to tell you is do not trust, and they're still amazing machines, don't get me wrong, but do not trust blindly the representation you get, because if you have some odd tooth or if you have some gingival margins that are not really well defined, or diastemas or rotations, sometimes the reformatting from the intraoral scanner will not give you the reality. In many circumstances, it's not that important, but in some it is. That's why sometimes people have a problem with their aligners, they don't fit or something happens, and they fit on the model but they don't fit in the mouth, because probably there was either an error in printing, which is different, but probably also maybe the scanner made some reformatting error or assumptions and gave you a model that is not exactly the reality. They are great machines, they're fantastic. The problem is the reformatting is software based, and obviously sometimes they're prone to errors once in a while. So this is good for part one, and we'll continue in part two to discuss the scanning process and the 3D printing.